Hey everybody, welcome to our next unit where we are talking about electrons and the periodic table. Now, in order to understand where electrons are located, how much energy they have, it's going to be very closely tied to the structure of the periodic table. It's kind of crazy that the periodic table is arranged in a way that lets us understand the structure of the atom and where all of the electrons are located. So we're going to kind of bounce back and forth this unit between talking about the structure of the periodic table and talking about electron configurations. So our last unit was all about the structure of the atom itself, and now we're really going to dig into the detail of where are the electrons, how much energy do they have, and how do they help determine the properties of that substance. So you are either going to be doing a periodic table activity with me tomorrow, or you'll have just finished that periodic table activity and now we'll be taking these notes. Either way, hopefully that activity that we did in class will help sort of tie together all of these ideas for you. So, our modern periodic table, where did it come from? Well, it started off back in 1869 with Mendeleev and Meyer. They were the first ones to organize the periodic table into columns. And these columns had elements with similar properties, which was kind of interesting and one of the first times that this was done. In order to organize these into columns, they ordered the elements by increasing atomic mass. You might think that the periodic table today is still organized by increasing atomic mass, but we're going to take a closer look. It actually is not. What was really cool about Mendeleev and Meyer's organization of the periodic table is this is the first time where scientists actually recognized that there were elements that had not yet been discovered. Like there were holes in their periodic table where elements with a certain set of properties and a specific atomic mass should be, but they hadn't actually discovered those elements yet. Which correlates to that activity that we were doing where there was like a hole and a missing element in your periodic table. And based on the way that you organized it, based on the properties of that column and that period, you were able to figure out what that missing element was. Now imagine being able to do that for substances at the atomic level, like things that we can't even see at the atomic level, having to do it based on properties and measurable quantities that we can measure in the lab. Pretty impressive. Turns out that as the atomic masses were measured more carefully, that Mendeleev and Meyer's periodic table actually didn't work anymore. And in fact, maybe I should stop this here and let's go look at the periodic table together, you guys. Let's look at this periodic table here. Let me make sure my recording is showing it. Yes, it is. Good. Don't mind me. If we look at the periodic table down here around argon, okay? I click on argon. Argon's atomic mass is 39.9 AMU. And potassium's is 39.09 or 39.1. In other words, potassium's atomic mass is less than argon's. But according to Mendeleev and Meyer, potassium would have gone here where argon was, and argon would have gone here where potassium was if they were still organizing the periodic table by increasing atomic mass. And then there'd be a problem with that, right? Because over here in this column, group number 8 on the periodic table, these are called the noble gases. You probably remember that from middle school. These gases are non-reactive. These are non-metals. They are non-reactive. They have 8 valence electrons, very stable elements. Potassium is a metal, not a non-metal, it's a metal. It is a solid, not a gas, and it's super reactive. In fact, it explodes in water. So it wouldn't really make sense for this substance, potassium, to be over here with all of these stable gases. That's what I mean by these columns having similar properties. So if we were still organizing by increasing atomic mass, these two elements would be totally out of place. So along comes a guy named Moseley. And what Moseley figured out, oh geez, it took me right back to the start. What Moseley figured out is that if you organize the periodic table by increasing atomic number, the number of protons, instead of atomic mass, everything works out beautifully. all of those groups have similar properties. And that's what periodic law says. It says when elements are arranged in order of increasing atomic number, there's a periodic repetition of their properties. So now potassium falls into a group where those substances all have one valence electron. They are all metals, except for hydrogen up at the top. We'll talk about that later. They are all super reactive and explosive in water. So that's what's so neat about this, is that if we organize by increasing atomic number and further by number of valence electrons, this amazing shape starts to appear, and it allows us to make predictions about elements and how they're going to behave. It's really cool. Okay, so let's talk about this beautiful structure here. Up and down, these columns are called groups or families. Typically, I call them groups. You're going to hear me refer to this as group 1, group 2. I'm going to skip over this big group here in the middle. Group 3, 4, 5, 6, 7, 8. 8 main groups. When we are looking across at these rows, the horizontal rows, these are called periods. 1, 2, 3, 4, 5, 6, 7. So go ahead and label that on that periodic table up at the top of your notes page. Columns are your groups. Rows are your periods. Columns 1 through 8, skipping all of these little groups here in the middle. We'll talk about why in a little bit. And periods 1 through 7. These two horizontal rows right here actually fit up inside the 6th and the 7th period, so you don't need to number those separately. Okay, so now we'll go through each group, talk a little bit about the properties of that group. I think you guys should shade in the group on the periodic table on the left, so it really just sort of like hammers it home visually, as well as writing out the notes. So group 1 are known as the alkali metals. Now notice I did not color in hydrogen. Okay, hydrogen, yes, is in group 1, but no is not considered an alkali metal. In fact, it's a nonmetal. The reason why hydrogen is in group 1, even though it is not a metal like all of the others, is because it has one valence electron. And all of the other elements, lithium through francium, they all have one valence electron as well. They are all very soft and super reactive metals. In fact, they're so reactive that you don't actually find them in nature in their pure form. They would be in compounds. They react with the oxygen in the air and are oxidized, or they are found in salts. The word alkali means basic or base forming. These substances, when they react with water, actually form a base. Okay, moving along to group 2. These are called the alkaline earth metals, not to be confused with the alkali metals. These are also metals that are reactive, not as reactive as the alkali metals are, and also form bases. Just some interesting facts about some of the elements in this group. Magnesium and calcium ions, again, once they've lost 2 valence electrons and become ions, these are very important minerals in our body. And if I didn't say it already, everybody in group 2 has 2 valence electrons. Do you guys see the pattern here? On to group 3. Now, luckily, the next set of groups don't have special names. So we don't have to memorize names for these groups going across here. This is just going to be the boron family, then the carbon family, then the nitrogen family, and the oxygen family. So that's kind of nice. The boron family also contains metals. So the periodic table, group 1, except for hydrogen, group 2, all of these elements in between here, these are all metals. So most of the periodic table is made up of metals. We'll talk more about that in a little bit. Aluminum is a metal, gallium is a metal, indium. I don't even know the name of that element. Isn't that embarrassing? It's pretty bad. Should we go look? Yeah, let's go look. Oh, it's thallium. Duh, I knew that. It's late at night, you guys. All right. So, where was I? Oh, yes, PowerPoint. Oh my gosh. don't know why it doesn't take me back to where I left off. So some interesting facts here about the metals in this group. Aluminum is the most abundant metal on Earth. That's why aluminum is so inexpensive. Gallium is a metal, but it has a very, very low melting point. Like if you were to make a spoon out of gallium, and I'll link to this video separately in your schedule. If you were to make a spoon out of gallium, it would melt if you were like stirring it in your hot chocolate. That's how low the melting point is. So it's important to understand the properties of different elements because obviously we wouldn't want to use gallium to make our utensils out of. Everybody in group 3 has 3 valence electrons. On to the carbon family. Now, as we go across the periodic table, like I said, almost all of these are metals, right? Except for hydrogen. When we start to get over towards the right-hand side of our periodic table, we are going to start to see a blend of metals, and we get to are introduced to some non-metals, as well as these things called metalloids. So if we have things that are metals and we have things that are non-metals, a metalloid is something that is sort of a blend of metals and non-metals. They have properties of both metals and non-metals. And this group contains all 3 types of elements, both metals, non-metals, and metalloids. Carbon, very, very important to us as it is the basis of all life. Silicon is a metalloid. It's very shiny, like a metal, but it's also very brittle, like a non-metal, making it a metalloid. This is actually the substance that you guys used in the lab practical on the Unit 1 test, that shiny little rock thing that you found the density of. That was silicon. And everybody in group 4 has 4 valence electrons. On to the nitrogen family. Again, here we have a mix of metals, nonmetals, and metalloids. 5 valence electrons. Now it's very tricky. The last family with the easy name is the oxygen family. Now here we've lost our metals, right? Now we're in just the metalloid and non-metal territory. Oxygen, super important for us in chemistry because nothing can burn without oxygen. So anytime you're burning anything, it's a reaction with oxygen. So when we say combustion in chemistry, that's what we're talking about, something reacting with oxygen. And everybody in group 6 has 6 valence electrons. Group number 7, the halogens. Everybody in this group has 7 valence electrons, and they are all non-metals. They are super duper reactive. These are our most reactive non-metals, just like the alkali metals were our most reactive metals. And when you guys are in school, I'll show you guys some of these elements, and you'll see what I mean by what a metal looks like versus what a non-metal looks like. And I'll also show you how reactive some of these substances are. Halide means salt. And so when these substances bond with metals, they form salts. Sodium and chlorine is sodium chloride. That is a salt. Technically, any metal-non-metal combination in chemistry is considered a salt, but you're obviously familiar with NaCl as table salt. And we call those salts halides because the halogens are in there forming 1/2 of that compound. And then lastly are our noble gases. Group 8. Now everybody in group 8 has 8 valence electrons, which is what makes them so stable, except for helium. Helium only has 2 valence electrons, but it is also a noble gas because 2 valence electrons is enough to make helium stable. And we'll learn why that's the case when we learn more about electron configurations. I'll also link to a fun little video where you can see with the noble gases as you go down the group, the mass of the gases increases. And we often don't think about gases having mass, but they do. And xenon is a very, very heavy gas. So go watch that video afterwards. Okay. So here is where, if we were in school, I'd be showing you a couple of demos. And if I don't remember to show you when you come in, please remind me. Metals are shiny, malleable, smooth, typically solids, except for mercury, and very good conductors of heat and electricity. I mean, just think about the metals that you know and are familiar with. Think about iron, think about aluminum. I'll show you some other metals that maybe you're less familiar with, like magnesium we work with a lot, and zinc. You're probably also familiar with copper. The color of the metal doesn't matter. What matters is that they are, in fact, shiny, malleable, and conductive. You'll notice here that the metals are all in green, and so most of the periodic table is made up of metals, right? Remember, group 1 and group 2 are the alkali metals, this big group, these two big groups that we sort of skipped over in between. And then as we get to the right-hand side of the periodic table, we start to lose metallic character. We start to head into the non-metal territory. All of these elements here in orange, including hydrogen. Remember, we put hydrogen over there because of its one valence electron. All of these non-metals over here are sort of the opposite of metals. So they're not solid. Some of them are solid, but some of them are also liquid. Bromine is a liquid, and a lot of gases. So if they are not in the gaseous or liquid state, they tend to be brittle, dull-looking solids, as opposed to shiny solids like the metals. And these are not conductive. And like I said before, metalloids, like silicon, have physical and chemical properties that could make them metallic in character or non-metallic. Like silicon, shiny, lustrous, like a metal. It's also conductive, but it's very, very brittle, which is not a property of a metal. So these elements here, along this sort of stair-step area that splits this rectangle on the right-hand side, these right here are your metalloids. And you do not need to memorize which of these elements are the metalloids, but as long as you generally know the area where they lie and that most of the periodic table are metals and they transition across into the non-metals. And before you get there, you have substances called the metalloids. Now, these two big groups that we skipped over here, this first one, these are called the transition metals. And they are, if we were to number the periodic table 1 through 18, so like that's one way to number the periodic table, 1 through 18, the groups. Groups 3 through 12 are considered your transition metals. I like to think about it as they transition you from the left side to the right side of the periodic table. Usually what we do, though, is we just skip over them in terms of numbering. I like to number the periodic table just group 1, 2, skip over the transition metals, 3, 4, 5, 6, 7, 8, because then the group numbering corresponds to the number of valence electrons, which is really nice. The inner transition metals, also called the lanthanide and actinide series because of lanthanum and actinium, the elements where they begin, they actually fit up inside the transition metals, which is why they're called the inner transition metals. And there would be this break here, and you can tell by the atomic numbers that there's this break where you would go through this inner transition metal periods, or groups, I guess you could call them, to get across back over to the nonmetals. So I think, let's go back to the periodic table here. Nope, that's not what I wanted to do. It's easier to see it in here. There we go. Here's lanthanum and actinium. So if we're looking from cesium to barium, number 57, lanthanum, this here is your lanthanide series. And these stars are where these elements fit up inside the transition metals. Now, why they're bumped out like this has to do with their electron configuration. So this will make more sense once we finish up the electron conversation, then we'll come back to the periodic table again at the end of the unit. And I think that's it, you guys. Very good. Okay, so hopefully, both with the activity that you guys did with the periodic table, the demos that I'm going to show you in class, and these notes, you have a strong understanding of how the periodic table is organized, the names of the groups, the group numbers, and the period numbers. See you in class.